In this lecture, I'm going to cover some of the basic ideas from frequentist data analysis. This is the assumed background for reading the Bayesian statistics textbook, but it's also a good review of the basic ideas that we need in order to carry out null hypothesis, significance testing, and those kinds of things that are standardly reported in journal articles. So the very first thing that we do when we collect some data is that we assume that the data are coming from some distribution. So let's take a very simple case. Let's assume that the data are independent. So each data point, each of the n data points is independent of every other data point. And let's assume that the data are coming from some distribution like a normal distribution, which has some parameters mu and sigma, which are unknown to us and will forever remain unknown to us. And what we want to do first when we collect such data is to obtain an estimate of the mu and sigma parameters. We do that through these estimators, mu hat and sigma hat squared. These estimators give us a way to obtain a rough idea of what these parameters might be given the data that we have, right? So these we estimate through the sample mean, which I'm going to refer to as x bar, and the sample variance, which I'll refer to as s squared. So the square root of this would be s, and that's the standard deviation from the data, right? So the sample mean and the standard deviation are two important estimates that we get from a data set, and we use these estimates for further statistical inference. It could be just estimation. Maybe we just want to estimate these parameters and draw our inferences from those estimates, or we want to do something more with them, as I will just explain, right? So the estimate for this, the variance has, you might see two different, formulas for those. So one divides by n, the other divides by n minus 1. The division by n minus 1 is to eliminate a bias in the estimate, but really when the sample size is large, when n is large, it's not really going to matter that much whether you divide by n or n minus 1. I just mentioned this difference here because you will see these two equations in different textbooks, and R always uses this formula dividing by n minus 1 because this is an unbiased estimate of the variance. Okay, so what good are these estimates of the sample mean and sample variance? Well, one very important application of these parameter estimates is to carry out null hypothesis significance testing. And what lies behind the null hypothesis significance test is the central limit theorem, which states the following. The central limit theorem states that if the data are coming from some particular distribution with some particular mean and standard deviation, right? So the example that I'm using here, and if the sample size is large enough, then if you were to repeatedly compute the sample mean by repeatedly collecting data from the same population, repeatedly collecting data and repeatedly calculating the sample mean each time, then what would happen is that the distribution of the sample means under this kind of repeated sampling would be guaranteed to be normal, and it would have the form right? So it would have the true mean for that distribution would be mu, and the standard deviation for that distribution would be what's called the standard error, sigma over square root of n. So what this is actually saying, what the central limit theorem is saying, is that if you were to carry out the same experiment over and over again, for example, let's say you take n independent data points in one experiment, calculate the sample mean for that one experiment. So I'll call that x bar 1 to represent the first experiment that we did. Then we do the second experiment, collect new data, independent and identically distributed data, calculate another sample mean, right? And keep doing this over and over again, let's say 1,000 times, right? Let's say you do this 1,000 times. The distribution of these means is going to be normal, and the underlying mean for that normal distribution would be the mean that produced the data. Remember that we are assuming that the data were coming from a normal distribution with mean mu and standard deviation sigma, and the standard deviation of these means, the distribution of these sample means, would be this standard error here, sigma over square root of n. So what the practical implication of this is that when we when we do a single experiment, just one experiment, we compute a sample means, right? We compute a sample means. We compute a sample standard deviation. We estimate these two parameters, and with these two quantities and knowing the sample size, which of course we decided on, what we can assume is that the distribution of the means under hypothetical repeated sampling. Remember that we did only one experiment, okay? So from this one experiment, we can describe the distribution of the sample means under repeated sampling. That's the big deal of the central limit theorem, and it is this central limit theorem that allows us to carry out the null hypothesis significance test, as I will now explain. Now, one important thing about the central limit theorem is that it allows us to get an estimate of the standard error, which tells us how variable the sample mean would be under hypothetical repeated sampling. And we can get that estimate by computing the standard deviation estimate and dividing by the square root of the sample size here. Now, one important fact that emerges from the central limit theorem is because the distribution of the sample means is normal, right? So what we know from the central limit theorem is that the distribution of the sample mean under repeated hypothetical sampling can be estimated in the following way. From the single sample mean that we have and the single standard deviation that we have, we can get an estimate of the underlying distribution of the sample means. So I'll just draw this distribution like this. And so what we get from our single sample is the fact that the distribution is centered around some mean value, and our best guess of that mean value is the sample means, okay, given our data set. And the standard deviation, the spread of this distribution, is described by this estimate, the standard error. Now, we know the properties of a normal distribution. What we know is that if you go plus minus 1.96 times the standard deviation to the left and right of the mean of the distribution, 1.96 times in this direction and minus 1.96 times in the left direction of the standard deviation, we cover 95% of the area under the curve, right? This covers 95% of the area under the curve. So what is the standard deviation here? The standard deviation is the standard error, right? This standard error is what we're talking about here, right? So we can, given our single sample and given our estimate of the standard error, we can actually describe, or we can delineate or specify a so-called 95% confidence interval. 95% confidence interval that covers 95% of the area under the curve. So what does this confidence interval actually tell us? That's an interesting question, and it has a very strange answer, right? But one thing that the confidence interval does tell us, and that's a useful piece of information, is that it's giving us some indication of how variable the sample mean, not the mu parameter. Remember that the sample mean is an estimate of the mu parameter, right? But what the sampling distribution of the sample means is telling me, and what this 95% confidence interval is telling me, is how variable the sample mean would be under hypothetical repeated sampling. So that's a useful thing to know from the confidence interval. If this interval is wide, then we have a lot of potential variability in the sample mean when we run the experiment repeatedly, if we were to run the experiment repeatedly. And if the confidence interval is very tight, that tells us that under repeated sampling, we would get very little variability in the sample means. Obviously, intuitively, it makes sense that we would prefer to get an estimate of the sample means with a tight interval, confidence interval around it, and we would not be super excited to get a confidence interval that is very, very broad, right? Because it has very high variability in the sample means under repeated sampling. This is an idea that will become more important when we talk about statistical power, right? Because this is a high statistical power situation and this is a low statistical power situation. So that's an important takeaway from the central limit theorem, that we can actually describe this 95% confidence interval, and the confidence interval can give us some indication of how variable the sample means would be under hypothetical repeated sampling. I'm going to also explain now what the 95% confidence interval technically means, and that's the next topic. So now let's talk about what the 95% confidence interval actually means technically. What it actually means is that if you were to counterfactually carry out the same experiment over and over again, and every single time, if you were to compute the 95% confidence interval in the way that I just described, plus and minus 1.96 times the standard error around the sample mean, then 95% of those counterfactually computed confidence intervals would contain the true mean of the underlying distribution that produced the data, right? So I'll just come back to this code in a moment, but let me show you a simulation that illustrates this idea. On the x-axis, you're seeing some 100 simulations, and each time what I'm doing is I'm collecting some data from a standard normal distribution, so mean 0, standard deviation 1, and computing the 95% confidence interval each time. So you can see that because of random variability in the data, I'm getting a different confidence interval each single time. And what's interesting about this plot is that 95 of these 100 confidence intervals contain the true mu 0, because the data are coming from a standard normal. 5 of these intervals, or approximately 5 of these intervals, because this is just a simulation, so it could be 5 or 6 or 4 or something, right? There are 5 intervals that do not contain the true mean that produced the data. Like this, for example, this one here, all these bold-faced bars are the ones that do not contain the true mean. That's what the meaning is of a 95% confidence interval. The 95% in the 95% confidence interval refers to the property of the confidence interval under hypothetical repeated sampling. So when you do an experiment, you compute only one confidence interval. Now you don't know which one of these confidence intervals you've computed, right? Either it contains the true mean or it doesn't contain the true mean, right? So you can't make a probability statement about the probability of the true mean being contained in the confidence interval, right? So you cannot say something like the probability that the true mean lies between some lower and upper bound is 95%. This statement is not possible to make in the frequentist paradigm. Impossible to make. Why? Because such a statement implies that mu has a probability density function associated with it. But mu is a point value. It's not a random variable. It doesn't have a PDF associated with it in the frequentist paradigm. Therefore, one cannot make this kind of statement about the properties of the property of the 95% confidence interval, one particular interval. You cannot talk about that one particular interval, this lower and upper bound from one single sample, as representing the probability of it containing the true parameter mu. What the 95% in the 95% CI means is that it's referring to the procedure of repeatedly running the experiment and the properties of those hypothetically generated confidence intervals under hypothetical repeated sampling. It's a very weird meaning, and one doesn't actually know what to do with it. But as I pointed out earlier, one useful interpretation of the confidence interval, the frequentist interval, is that it gives us some indication of the uncertainty of the sample means under hypothetical repeated sampling. And this has huge implications for us when we try to interpret the results of a hypothesis test, as I will just explain. So coming back to this little simulation here that illustrates the meaning of the 95% confidence interval, what I'm doing here is that I'm just running 100 simulations from a particular distribution, so a standard normal distribution with mean 0, sigma, standard deviation 1, right? And then what I'm doing is I'm computing the lower and upper bounds of the confidence intervals repeatedly, and then what I do is I check how many or what proportion of those 100 confidence intervals contains the true mean. So what you can see is that roughly 95% of those confidence intervals contain the true mean. So notice here that I'm using the sample mean plus minus 2 times the standard error. Earlier I had said that 95% of the area under the curve would be covered by plus minus 1.96 times the standard error. That's technically true, but I just used 2 as an approximate value here, so it's not going to change things very much. And so this code actually produces 100 confidence intervals, 95% of which contain the true mean, and that's represented by this calculation here. So that's all what this piece of code illustrates. And actually I use this code to generate this figure as well, because all these 100 confidence intervals that you see, they were generated using that for loop. One important mistake that one often sees in published papers is the incorrect calculation of the confidence interval. So this typically happens when you have repeated measures or dependent data, and what happens is that we forget the crucial assumption that the data are assumed to be independent. Okay, so let's see an example that illustrates the incorrect calculation of the 95% confidence interval. So this is a data set from a well-known paper in psycholinguistics on object and subject relative clauses in English by Grodner and Gibson, 2005, their experiment 1. So in this experiment, we have 42 subjects who read 16 items in 2 conditions, object gaps and subject gaps, and the dependent variable is reading time at a particular region in the sentence. So what we want to do now is compute a confidence interval for the object gap condition and a subject gap and the subject gap condition. So let's try to do that. And what I'm going to do first is to compute it incorrectly. Okay. So what we do is let's first take a look at the structure of the data set. Okay. So what I said was that there are 42 subjects and 16 items and 2 conditions, and these are in a Latin square design. Therefore, what this means is that each of these 42 subjects, right, so there are 42 subjects, you can see the numbers here, is seeing each of the 2 conditions 8 times. So each subject is delivering 16 data points, 8 object gap condition data points and 8 subject gap condition data points. The implication of that is that these data points, these 8 data points that I'm getting from each subject in each condition, they are correlated. They're no longer independent, right? I can't just ignore that detail when I compute the confidence interval, okay? So, let's first just ignore this detail and compute the sample means. Okay, so there are the two sample means that we have for the object gap and the subject gap, and we can also compute the sample standard deviation. So this is now a mistake, right? This is a mistake because we're calculating the standard deviation over the entire data set which contains correlated data. We are not computing the standard deviations for each of the two conditions correctly, because we are assuming that each of the data points in each of the two conditions is independent of every other data point. We know that that's not true, right? So these two standard deviation estimates of the two conditions are actually wrong. And as a consequence, any further calculation that we do of the standard error and the confidence interval, that's going to be wrong, right? So let's do it anyway, right? So the sample size is 42, right? I said there are 42 subjects, so we're going to compute it over subjects. So once we compute the 95% confidence intervals, let's say just for the object gap condition, right? We get two confidence intervals, lower and upper bounds. These look fine because I based them on my standard error calculation, but the standard error estimate is based on my incorrectly computed standard deviation on the unaggregated data, right? Therefore, this confidence interval is actually wrong, right? Now, how would I compute the correct confidence interval for this situation? The way to do that would be to first aggregate the data such that I have those 8 data points that I have from each subject in each condition. Those 8 data points are compressed to an average data point for each condition, so that for each subject in each condition, now I have only one data point, which is the average of those 8 data points. And that's what you see here. Once I run this aggregate command here, if I look at the number of data points I have for the 42 subjects, in each of the two conditions, instead of seeing 8s here, I'm seeing 1s. And the reason I'm seeing the 1s is that I've taken the average of those 8 data points, compressed the data into one data point for each subject in each condition. Now, if I just focus my mind on the object gap conditions, right, on the object gap condition, what I have is an independent data point from each subject. So I have 42 data points in total for the object gap condition, and each of those data points is independent of the others. Now I can compute the standard deviation correctly. Okay, so I'm going to redo the calculation. The sample means for the object and subject gaps do not change. Whether you aggregate or not is not going to matter if the data are balanced, as is the case in this data set. In this data set, there's not a single missing data point. I have 42 subjects, 16 items, so 8 data points from each condition. So whether I take the aggregate and then calculate the sample means for the two conditions, or whether I take the unaggregated data and compute the sample means, I'm going to get the same numbers, right? If the data were imbalanced, had an imbalance in them, so that means if there were some missing data points there, then I would get different numbers depending on whether I aggregate or not. That's just a side note, okay? So here's my sample means. It looks all good. And now I compute the sample standard deviations, but this time these are correct estimates now, correctly computed estimates, because I'm doing this on the aggregated data, right? And now I can compute the lower and upper bounds of the confidence intervals, and these would be the correct calculations for the confidence intervals. It's important to calculate the 95% confidence interval correctly, because people often try to interpret the interval in terms of a hypothesis test. So often what will happen is that what is of interest in a hypothesis testing setting is that if I have two conditions like the object gap, which I'll call object relative, and subject gap, which I'll call subject relative, the thing of interest, in that particular experiment that I'm talking about is the difference in reading times between the two conditions. And so what one wants to do in this kind of situation is to calculate the difference, the average difference in reading time between object and subject gaps. I'll call that estimate D. Okay, and what we want is a 95% confidence interval over that difference, right? So I could estimate the standard error using the aggregated data. So what I would get in effect is a 95% confidence interval that is centered on the difference between the two conditions in the sample that I have, and two numbers, lower and upper bounds, that represent the 95% confidence interval. So the reason it's important to compute these intervals correctly is that these intervals are often used to carry out a significance test. What that means is that if 0 lies outside this interval, if 0 is here, for example, then I would claim that I have a significant result, right? I have a significant difference between the two conditions. If 0 is inside this interval, then I would claim that I do not have evidence against the null hypothesis. So the confidence interval does have a correspondence with the frequentist null hypothesis significance test, but only if the confidence interval is correctly computed, right? So if you compute the interval incorrectly and you end up with some wild interval like this, right? Now, if 0 is included in this interval, then you have drawn the wrong inference as regards the hypothesis test. Okay? So you have to be careful about how you compute the confidence interval, but you can actually draw a correspondence between the confidence interval and the null hypothesis significance test, which I'll just talk about in a moment. One side note that I want to make here is that people often use the Bayesian 95% credible interval in this manner to carry out a hypothesis test. This is technically not correct unless you know the frequentist properties of the Bayesian credible interval. But normally in the classical Bayesian framework, we don't actually talk about the frequentist properties of the Bayesian credible interval. We could, of course, do that, and some people actually do it, but you would have to establish that it does have the frequentist properties that you would expect. So normally we do not use the 95% credible interval in the Bayesian paradigm to carry out a significance test. Okay, so it would be wrong in general to claim that if 0 is not included in a Bayesian credible interval, then you have evidence against the null. In order to argue against the null or in favor of some hypothesis, you'll have to carry out a Bayes factor analysis, right, which I'll talk about later in the Bayesian course. Bayes factor analysis, or you have to do something like k-fold cross-validation or something like that, right? K-fold cross-validation. So these are the ways that you would establish evidence for one model over another model, but in general, one would not use the Bayesian interval to carry out a frequentist null hypothesis significance test. So this discussion about the 95% confidence interval and hypothesis testing brings me to the central workhorse of frequentist data analysis, the t-test, right? So the null hypothesis significance test. And so what this t-test basically does is the following, right? So the idea is that we start with the central limit theorem that I mentioned earlier. We know that the distribution of the sample means under repeated hypothetical sampling is normal, provided the conditions are met that I mentioned earlier. And the center point of that distribution is the parameter mu that produced the data, and the standard error of the sampling distribution of the means under repeated sampling is it's computed using this standard error formula, right? So this is what we know from the central limit theorem, and this is what allows us to carry out the null hypothesis significance test. And the starting point is that we set up a null hypothesis. We say that we assume that the true mu has some specific value, which I'm calling mu sub 0, and in this particular example I'm just using mu equal to 0, okay, because that will often be the hypothesized value, because normally we'll be talking about differences between two conditions, and so the standard null hypothesis there, at least in psychology and linguistics, is that the difference in means between the two is 0, okay? So that's why I use 0 here. So we set up a null hypothesis for the mu parameter, okay? And then the question that we ask is, when we've computed the sample means, how far away is the hypothesized mean mu 0 from the sample means, right? So all we do basically is we want to quantify this distance, the distance between the sample means and the hypothesized mean, right? So the t-test is just a distance calculation, right? Now, one issue with this distance calculation is that depending on the scale of the data that you're working with, a large distance or small distance really would depend on what the range of variation is in the data, right? How variable the data are. If there's a huge amount of variation in the data, then even a large distance could be considered a small distance. And if there's very tiny variation in the data, even a small numerical value could represent a large distance. So what we want to do is we want to somehow standardize this distance such that we have an even, playing field regardless of what the range of variation is in the data. So what we can do is we are going to standardize or normalize this distance by dividing it by the standard error. Okay? And so this calculation gives us what's called the observed, or what I call the observed t-value, right? We get this observed t-value from the data, and really what this observed t-value is doing is it's quantifying the distance. It's quantifying the distance between the sample mean and the hypothesized mean in standard error units, right? So when we calculate this t-value, what we are saying is that the distance between the sample mean and the hypothesized mu value is t standard errors, okay? And so the hypothesis test basically now amounts to saying the following: if this t-value is large, then we will reject the hypothesis that the true mu is mu 0. And if the observed t-value is not large, then we won't reject. No, we won't be able to reject the null hypothesis mean. Okay, that's the basic idea now. Okay? So where do we go from here? Well, remember that this calculation that I'm just doing here is based on a single sample here. But I could repeatedly run this experiment and repeatedly calculate the sample mean and the standard error based on the sample. And in doing so, what I would end up with is a distribution of observed t-values. So the t-values that I could observe under hypothetical repeated sampling would also have some distribution associated with them. And that distribution is called the t-distribution, and is parameterized by something called the degrees of freedom, which is the number of data points minus 1. You have to remember that I'm assuming here that these are n independent data points. I'll come back to this point later on, okay? N independent data points. So this t-distribution actually represents the distribution of these observed t-values under hypothetical repeated sampling. And so this t-distribution can be described mathematically, right? So I'm not going to write down the formula, but this t-distribution looks very similar to the standard normal distribution with mean 0 and standard deviation 1, as I will just show you. So the observed t-value is also coming from a particular probability density function, which is the t distribution. And that t distribution is parameterized by the degrees of freedom, which is the sample size minus 1. And we can write down the random variable that represents the t distribution, the random variable that produced the observed t values under hypothetical repeated sampling in this manner here. Capital X bar represents the sample mean that we would compute repeatedly. The mu sub 0 is our null hypothesis value, and I can write it as mu as well. I mean, it's understood that this is the null hypothesis value here, and the standard error would be in the denominator because that's the way we normalize the distance, right? So this is a transformation of the statistics from the samples that we would get under hypothetical repeated sampling, and this gives us the distribution, the random variable t, which we can characterize as coming from a t distribution with degrees of freedom n minus 1. So as I mentioned, the t distribution is very similar to the standard normal distribution, and you see this here for a relatively small sample size, maybe something like 20 or something. 21 is the sample size here, so degrees of freedom are 20. So what you should notice is that in this figure, the t distribution, which is the solid line, has somewhat fatter tails, and the standard normal distribution has somewhat narrower or flatter tails and is a higher density in the center point here. So the total area of the curve in both distributions will sum to 1, but the t distribution for lower sample sizes like 21 or something would have slightly fatter tails than the standard normal distribution. But if we increase the sample size to much larger values, I don't know what I've used here, something like, what is it, 2000? I can't actually see, 1000 or 2000, doesn't matter. But for some large n, what you'll see is that the two distributions start to align, right? So the t distribution becomes more and more like the standard normal distribution. And in fact, as n goes to infinity, right, if you keep increasing the sample size, the t distribution will approach the standard normal distribution. Okay, so the hypothesis testing procedure is now straightforward, right? We set up a null hypothesis value for mu. We compute the sample mean. We compute the sample standard deviation. We know the sample size, assuming independent data. We can compute the standard error estimate. And once we know the standard error estimate, we can compute the observed t-value. And the observed t-value now can be compared to the distribution of t-values for that particular sample size. So suppose I'm running an experiment with sample size 42, as in my example earlier, right? So let's say with the sample size 42, then the reference distribution that I'm going to be looking at is the T41 distribution, right? And then what I'm going to do is I've set up a null hypothesis that the difference between the two conditions is 0. That's my hypothesized value for the difference. And what I want to know is where along the x-axis does my observed t-value lie? If my observed t-value lies far away in the tails, either side of the distribution, then I would want to reject the null. If it lies near 0, then I would not want to reject the null. I don't necessarily want to accept the null, but I would fail to reject the null. Okay? So that's basically the procedure now, right? Either reject or not reject. And that brings us to an important point about how we decide when to reject. So the way we will do that is that we will set up some rejection points in the t distribution. And so this is the lower bound and the upper bound of the rejection points, right? So these we will call the critical t-value. I said critical t-value and not critical t-values because when the distribution is centered on 0, the t distribution is symmetric. So whatever number I have here, I have the negation of that number here. Right? So the absolute critical t value, right? Let's just call it the absolute critical t value will be one number. Okay. So we set up this rejection point here such that, right? So here's the way we decide what the rejection point should look like, such that the area under the curve to the left and right of those rejection points sums up to 0.05. Okay, so what that means is that we would have a 5% probability. We have a 5% probability of landing in this region or in this region. Right? That's how we set up the rejection point. So the upshot of all this is that once I have computed my observed t-value, if the observed t-value lands in this rejection point here in the rejection region or lands here, I would reject the null. If my observed t-value lands anywhere within this non-rejection region, I'm just making this terminology up, okay? So it's not a standard terminology. In this non-rejection region, then I would fail to reject the null if my observed t-value lands anywhere here. That's the basic logic of the t-test and more generally the null hypothesis significance test. So if you think about the hypothesis testing procedure, we basically make a decision about whether to reject the null or not based on the rejection points that we decide on, the critical t values for a given t distribution with some particular degrees of freedom. So that's what I'm calling the rejection region here. And what we report in a data analysis in a published paper or something would then be the observed t-value with the given degrees of freedom and the associated p-value, which tells you the probability of observing that particular observed t-value or something more extreme under the assumption that the null is true, right? So if the null hypothesis is represented by a distribution, t distribution that is centered on 0, right? And your observed t-value is some number on the x-axis like this one. Let's say this is my observed t-value. Then the p-value that we will report is the probability of observing this observed t-value or something more extreme in both directions of the t distribution. So we would take the negation of the observed t-value, and so these two numbers would be identical as absolute numbers. So we're just looking to the left and right of the distribution from the absolute observed t-value. And if we sum up the probability represented by the area under the curve here with the probability under the area under the curve here, this would constitute the p-value, and we would then report, for example, in the the example I'm working with where I have degrees of freedom 41, I would report something like my observed t-value is 3.1 with some p-value equal to whatever it turns out to be. Okay, so we can look up the corresponding p-value by using one of the dpqr family of functions as discussed in the foundations lecture in chapter 1. Okay, so this is the information that I would report, and in addition what one generally reports is the difference in means that you observe. So let's say it's minus 102 milliseconds, and that would be the difference in means between the two conditions, right? Subject minus object relative, and then 95% confidence interval. So those two bounds would tell you the range of the 95% confidence interval. So that's the information that one would be reporting. And the important thing to remember about the p-value is what it does and does not tell you, right? So the p-value is telling you the probability of observing an observed t-value as extreme as this one or something more extreme under the assumption that the null is actually true, right? So the p-value is not telling you the probability of the null hypothesis being true. So you can think of the p-value as roughly representing the probability of observing the absolute value of the t-value or something more extreme under the assumption that the null is true, right? This is not equal to the probability that the null is true, obviously, right? So you have to be careful about this, and this is a common mistake that people make. Another thing that the p-value is telling you is how much evidence you have against the null hypothesis. It's not giving you evidence directly in favor of the specific alternative that you want to argue for, right? So it is answering a question, but it's not answering the research question that you have, which is how much evidence do I have for the particular research hypothesis that I have. So in the case of the relative clause example, the research hypothesis is that subject relatives should be easier to process than object relatives, right? That would be one way to characterize the theoretical claim. And so if the difference in reading time between the two conditions is minus 102 milliseconds, let's say, so in that case, we don't have, through the p-value, we do not have direct evidence for the claim that subject relatives are easy to process than object relatives. Rather, we have strong evidence against the null hypothesis that there is no difference between the two conditions. Okay? Another important thing to remember about the p-value is that if you get a p-value that is larger than 0.05, so that means your observed t-value lands within the non-rejection region, right? It lands inside the critical t-values. In that situation, in general, you cannot argue that you have evidence for the null hypothesis. So it's a very common mistake to get a p-value that when you get a p-value larger than 0.05 to argue that you have found evidence for the null. That's not necessarily true. That could be argued in certain cases, in certain situations, but I'll talk about those later on. So you have to be careful about what the p-value does and does not do for you, and as long as you don't get misled by the meaning of the p-value, you're good to go, right? One important thing I want to mention is that people often treat the p-value as giving you some indication of whether you found something true about nature or not, right? That's not necessarily what the p-value will give you. You could get a very low p-value, but you may still be unable to replicate that result in future studies. So one takeaway from that is that the only way, this doesn't matter whether you're a Bayesian or frequentist, the only way that you can get strong evidence that an effect is present in nature for some particular phenomenon is by being able to consistently replicate that result in repeated experiments. Right? That's the only way to find out. These p-values and any other kind of statistic that gives you evidence for or against a particular model, these are indications that you can, get some information from, but they're not necessarily pointing you to the truth. And that's true for Bayes factors and other kinds of model comparison tools as well. Some basic R syntax that you should know for conducting a paired t-test or one sample t-test, they're both the same thing, is the following. Okay, so going back to my data set, my example from the Grodner and Gibson experiment 1 data, where we are comparing object and subject relatives, what one primitive way to do a t-test which will work is to take the aggregated data. So this is aggregated over the subject so that all the multiple data points I have from each subject in each condition have been aggregated to the mean, right? So I have only one data point from each subject in each condition. So what we do is from the object gap conditions, we extract the reading times. So that would be a vector of 42 data points, right? That I'm saving as the object OR. And similarly, I save the subject gap data points, the aggregated data for the 42 subjects in this SR vector. And then I can compute the difference between the OR and SR vectors. So remember that these two vectors, they consist of 42 cells, and each of the cells in the object and subject gap vectors are coming from the same subject. So if I do a cell-wise subtraction, right, from the two vectors, I will get this difference vector, which tells me it will have length 42, and it will tell me what the difference is, estimated difference is between the object and subject gap in each of the participants, each of the 42 participants in the experiment. So I have a vector of 42 difference scores, and then what I can do is I can run the t.test function on the difference score, right? And what that would give me is the observed t-value, which is 3.1 here, right? And notice that I can ignore the sign of this t-value, because if instead of subtracting SRs from ORs, if I had subtracted SRs from ORs, I would get the opposite sign for the t-value. Okay, so the sign actually is only telling me the direction of subtraction that I had done when I created the difference score. So that's one thing I get, the observed t-value. I get the degrees of freedom, which is 42 minus 1, the p-value, which I just discussed, and then the 95% confidence interval, which I have explained the meaning of, and the estimated mean of the difference between the two conditions. Okay, so this summary gives you all the information that you need to report your results in a paper, for example, right? So that's how the one sample or the paired t-test would work. I mean, you could have done the same data analysis as a paired t-test. It would be exactly the same thing. So here what we are doing is we are running a paired t-test where the first vector, so we don't put in just one difference score vector. We have a vector for the object relative reading times, a vector for the subject relative reading times. So the subtraction is done internally by the t.test function. When you specify paired equal to true, the t.test function knows that this is paired data. That means the 42 cells in the OR and SR vectors, they're all representing data from the same subject, right? Each of the cells is representing the mean reading time, estimated mean reading time for each of the 42 subjects, right? That's the purpose of the paired equal to true specification in the paired t-test, this one here, okay? And as you'll see, the output is exactly the same as we had in the one sample t-test, where I was using a different score instead of having OR and SR here. Now, as I mentioned earlier, if I reverse the order of SR and OR, so if I had SR first and OR second, then the t-value would be the opposite sign to what it is here, and the sample mean would be the opposite sign. The confidence intervals would be also the opposite sign, but the p-value would be unchanged, and the absolute value of the observed t-value would be unchanged as well. The absolute value of the difference of the means would be unchanged as well. It's just the sign would change, right? Okay, so these are two important pieces of code that you must know in order to be able to carry out data analysis for repeated measures data. The critical thing to remember is that if you have repeated measures data, you will have to aggregate the data before we can do the t-test. Otherwise, you're going to get incorrect analysis. So here's an example of an incorrect analysis, and you'll be surprised to hear that very often people publish papers with this kind of incorrect, analysis where they forget or do not know to aggregate the data. So here, what I'm doing is I'm extracting the reading time for the object and subject relative conditions, but I'm not doing that from the aggregated data, but rather from the unaggregated data. Okay, so I have all the repeated measurements here. Okay? You'll see the consequences of that. Then I do the same thing. I extract the difference vector. R will do it for you. So R is assuming that you know what you're doing. R doesn't care whether you got this methodology correct or not. It assumes that you know how to do a t-test correctly. So you can easily make all these steps and get a t-value and a p-value printed out from the t.test function, but it will be completely wrong. So let's run a t.test function on the difference score on the unaggregated differences, right? And now what you find is that the t-value is even bigger, p-value is even smaller. The difference for the means is the same, because as I mentioned, it doesn't matter when you're computing a difference of means from the data. It doesn't matter whether you aggregated it or not if the data are balanced, right? So the confidence interval will be wrong, and the t-value will be wrong, and you can actually eyeball the output and see right away that there is something wrong with this analysis, because you had 42 subjects. How come you have such a large degrees of freedom, right? It should have been 41, right? So this is a good sanity check to establish whether you actually did the analysis correctly or not, right? So this would be an incorrect analysis. Please don't do this kind of stuff. But I just wanted to demonstrate that, this can mess up your life very badly if you end up doing the wrong kind of analysis. Okay, so same situation here. Instead of different scores, I could have taken the OR, SR paired t-test and still got all incorrect, t-values and p-values. So you could end up drawing the wrong inference, if you're not doing the t-test correctly. All right, so that's the story with the t-test. Now, when we do a t-test or any kind of statistical null hypothesis significance test, we are, as I mentioned earlier, we're setting up a null hypothesis distribution like this solid black line here, centered on 0, and we are defining our rejection points. These are the rejection points in the null hypothesis distribution, and the area under the curve, these black shaded area under the curve in the null hypothesis distribution sums up to 0.05 by convention. And so the logic here is that if our observed t-value lands either here in this rejection region or in this rejection region, then we reject the null hypothesis. And if it lands in this non-rejection region, then we don't reject the null hypothesis. That's the basic setup here, right, of the null hypothesis significance test. So now I just want to quickly talk about the situation where the null hypothesis is in fact false, right? So let's try to build a little matrix here to represent what could happen, right? So one possible thing that can happen is that the null hypothesis might be true. Another possible situation is the null hypothesis could be false, right? These are two possible worlds that we could be in, and we don't know which world we are in. Otherwise, if we knew that the null is true or false, then we wouldn't need to do any statistics, right? No hypothesis test would be needed. So these are two possible worlds out there. We don't know which one we are in, okay? But what we do is that we will carry out a decision based on the statistical test that we do. So we would either reject the null or not reject the null, right? So these are two things that we can do. These are two decisions we can take based on our data and on the statistical analysis, but these are the two possible worlds that we could be in. Now, if we reject the null, if we reject the null and the null is actually true, then we made a mistake. This is a mistake, right? Similarly, if we fail to reject the null and it turns out that the null is actually false, and then here also we have made a mistake. So these are two kinds of mistakes that one could make, and these mistakes are called type 1 error, and type 2 error. Right? So type 1 error can be graphically visualized quite easily by looking at the figure that I just showed you, and I'll just draw it again. So that type 1 error is represented by a probability value called alpha, and it looks like this. Okay, so let's draw the null hypothesis distribution again, centered on 0 in my running example, and we define our rejection points, if you remember, such that the area under the curve to the left and right of these rejection points sums up to 0.05. This area under the curve is the type 1 error and is conventionally set at 0.05. The logic here is that when we do our statistical test, the probability of our incorrectly rejecting the null when it's actually true will be 5%. That's the meaning of this particular graphical summary of of type 1 error, or alpha error as it is called. Okay? Now, the interesting situation now is that what would happen if the null was actually false with some particular value on the x-axis for the t value, right? So the t value could be, for example, let's say 2. Okay, let's just say that the t value that represents the truth about the world is 2. In that case, and not 0, okay, so it's not 0 but 2. So in that case, the true distribution is the blue distribution here, right? It's centered on 2, right? So now we are talking about two distributions at the same time. This distribution here represents the null hypothesis distribution, and this distribution here represents the true distribution for a particular value of the parameter. Okay, so with some we could imagine a situation where the true distribution is centered on 2 in the t distribution and not centered on 0. So in this case, in the blue distribution, the null is clearly false. So now the question that one can ask is, what is the probability of not rejecting the null when we are talking about this distribution? The probability of not rejecting the null when we are talking about the blue distribution is the area of the curve in the non-rejection region, which was defined with reference to the null distribution. Right? So these are the critical t values that we defined with reference to the null distribution. But the area of the curve I'm sketching out right now is the probability of my incorrectly failing to reject the null when it's actually false. Right? So that probability is characterized by convention by the letter beta, right? The Greek letter beta. So one interesting thing about this is that if this blue shaded region represents type 2 error probability, which is the probability of failing to reject the null when it's actually false. What is the probability of correctly rejecting the null when the null is false? Right? That probability would be 1 minus beta. And that probability is the probability under this blue curve, the probability, the area under the curve in this blue curve to the left and right, of the blue distribution, which represents the situation where the null is false. Right? So this probability 1 minus beta is called statistical power. Right? So we'll just call it power here, but it refers to statistical power. And so now you can see what is going to happen now when we run the experiment with high power versus low power. So I'm going to talk about that next. This is the significance of this figure that I'm showing you here, because what this figure does is it displays the relationship between type 1, type 2 error, and by implication statistical power. Right? So the black colored regions under the null distribution represent the type 1 error. I don't know what color this is, maybe orange, right? Orange or yellow, I don't know, I'm kind of colorblind. The orange color is representing type 2 error, and if you think about it, what you really want when you do an experiment is to keep your type 1 error low. You don't want to make wrong decisions. So you want to keep your type 1 error low. That means you want to keep the probability of your incorrectly rejecting the null when it's actually true low, and we conventionally set it to 0.05. And you want to keep the type 2 error as well as low as possible, right? So what that means is you want this orange shaded region to be as small as possible, right? As practically possible. So by making the orange colored regions as small as possible, what you're doing is you're making statistical power larger, right? And why do you want to make sure that your type 2 error is low as well? Well, because you don't want to be in a situation where you fail to reject the null when the null is actually false. That's also a mistake, and you want to avoid making those mistakes. So the optimal situation that you can be in is to have low type 1 error, 0.05 for example, and low type 2 error, or high statistical power. So the ideal situation you want to be in is that you run a high power experiment where your type 1 error probability is low and your statistical power is high as you can make it. So that's what we'll talk about next. The important thing to understand here is that if you carry out a statistical test where your statistical power is low, that means the orange colored region is large, your type 2 error is large, in that situation, you're in a very unfortunate position when you fail to reject the null, right? Failing to reject the null there would not imply that you can argue for the null, because your type 2 error would be incredibly high. Okay? So that would be an invalid or incorrect inference to draw to argue for the null if you fail to reject the null when you have a low power setting. If you have a high power setting, that means your type 2 error is very low and you get a null result, that means your p-value is larger than 0.05, then you are in a good position to argue that you may have evidence for the null. Of course, we never know for sure, but you could be in a stronger position to argue for the null if you can establish in advance of running your study that your statistical power is high. Okay? So there are some very bad consequences to running an experiment with low power. And in fact, the frequentist paradigm was not really designed for running low power experiments. The frequentist paradigm works really well when you have a high power setting. It doesn't work so well when you have a low power setting, and it can lead to invalid inferences, as we see unfolding in many different fields, biomedical sciences, in psychology and in linguistics. We have replication crises one after another, and so one reason for that is the proliferation of underpowered studies being published in journals which would never replicate, because it's very hard to reproduce an accidental result that happened due to a misestimation of the parameter of interest. I will just talk a little bit more about that in a moment. So, but first of all, how would you compute power? So there are different ways of doing this computation. One approach is to do a quick and dirty calculation based on the power.t.test function, and I'm going to talk about that here. There are more sophisticated ways of doing this using simulation, but there's not enough time to talk about that. So I'll just stick to the simple case, and in fact this method works pretty well if you have some ballpark estimates of the parameters of interest. So power depends on three things. It depends on the effect size, it depends on the standard deviation, and it depends on the sample size, right? So once you have these three pieces of information, you can calculate power. Or if you have two of these three pieces of information, let's say effect size and standard deviation estimates, and you want to know what sample size you need to achieve 80% power, you can answer that question using the power.t.test function. So this is fairly straightforward here. So what we are doing here is that we first define what I've done here is that I've set n equal to null, and that's because I want to ask the function what sample size I would need in order to obtain 80% power. Okay? So I've specified some parameters. I've specified my parameter for the effect size. So let's say in milliseconds, 15 milliseconds, I've specified the standard deviation here for my experiment. So this is just a ballpark estimate I got from years of experience doing experiments with self-paced reading and eye tracking and so on. So reasonable estimate for self-paced reading, for example. I set up the significance level, that is the alpha level, type 1 error at 0.05, and power at 0.8. And so the question, and then I've specified that I'm doing a two-sided t-test on it will be a one sample test that is two-sided, right? So I'm looking at both sides of the distribution, like I was doing when I was explaining the t-test, right? And strict is just a parameter that ensures that you calculate the area under the curve in both locations. So power will be the area under this curve, the red curve here to the right of the rejection point here, and the area under the red curve to the left of this rejection point. So the strict equal to true means that I'm going to calculate both those areas and sum them up, right? Okay, so where was I? Yes, so here's my command. So once I run this command, I get an output which tells me what sample size I would need in order to achieve 80% power given those particular parameter estimates, right? You can also ask different questions like, for a particular sample size and a given effect size and a given standard deviation, what would be my power for the particular experiment that I want to run in the future? Remember that these power calculations are always with respect to what you will do in the future. You can't actually run the experiment and then compute the statistical power of the experiment that you have already done. That's called observed power, and that observed power is just a function of the p-value. This is discussed in a famous paper by two people called Honig and Heisey. You can just Google it, Honig and Heisey, right? And so They discuss the fallacy about computing observed power. So you should not fall into the trap of computing power on data that you have already collected, and you should not talk about the power of your actually conducted experiment. Power is always with reference to something that you plan in the future. Okay? So here's one very important adverse consequence of having low statistical power. This is what Gell-Mann calls type M error, M for magnitude. So imagine a situation where your true effect size is 20 milliseconds, standard deviation is 150, and sample size is, let's say, 25. Okay? People routinely run experiments with these kinds of sample sizes with standard deviations like these, and the true effect size might be 20 milliseconds for all we know, right? What would happen in such a situation is that your statistical power would be about 10%, which is very low. That means your type 2 error is 90%, okay? So if in this situation you were to repeatedly run the experiment, so here I've done it some 50 times, and each time you compute the parameter estimate plus a 95% confidence interval, right? What you will find is that in only a few instances would you get a significant effect. That means only in a few instances would you be able to reject the null hypothesis, right? These are 4 instances here. And in most other cases, the black circles that you're seeing here, they represent the cases where you fail to reject the null hypothesis, okay? So this figure is actually very revealing, because what it shows is that in the few cases that you do get a significant effect despite having low statistical power, those estimates are going to be strong overestimates. They're going to be really far away from the true value of the parameter, which is 20 here, right? So even if you get a significant effect under low statistical power, even if you get a significant effect, that estimate will be an overestimate or a misestimate, right? It could even be a misestimate in the wrong direction, right? That's a negative value over there, even though the true parameter is positive. So this is called type M error, and this is a very damaging consequence of running a low power experiment, that even a significant effect would be arising due to a heavy misestimation of the parameter. So the significance of the result is not super informative, because the maximum likelihood estimate of the effect, this estimate here, is way off from the true value. And you can imagine what the consequence of that would be. If you rerun the experiment to try to replicate the result, you're more likely to land in one of these situations where you fail to replicate the result, because these are lucky shots now, right? Based on extreme data points, extreme estimates of the sample mean. So you will not be able to replicate that experiment, and this is one of the reasons why we have a replication crisis. Many, if not most, of the studies that are published, even in top journals, they're severely underpowered, and they're lucky shot papers in the sense that the estimates were lucky shots that will never replicate. And so that's how we end up in an awkward situation that we can't replicate any of the published results. Okay? So now think about what happens if we were in a better situation with, let's say, 80% power, right? I've increased the sample size here, that would increase power. What will now happen is, if you repeatedly run the experiment, what will happen is, in most cases, those white triangles represent the significant effects. You will get evidence against the null, and only in a few cases you would not get evidence against the null hypothesis. And more importantly, in the cases where you do get evidence against the null, the evidence will be based on an estimate of the parameter that is pretty close to the true value of that parameter, right? So in that sense, the p-value and the significance test is actually informative now. So this null hypothesis significance test is only informative if you have high statistical power. If you have low statistical power, all bets are off. We don't really know whether we found a real effect or not. Notice that the null is still false in this case, right? It's just that we have a very bad estimate, overestimate of the effect, and we're not going to be able to replicate that, the significant result in a subsequent study. Well, probabilistically, we won't be able to replicate it. Okay, so that summarizes the main issues with type 1, type 2 error statistical power. And the main takeaway here is that when you run an experiment, you should aim to run an experiment with as high statistical power as possible. That's the major takeaway from this discussion. One other important detail with null hypothesis significance testing is that when you carry out more than one significance test on your data set, you are inflating your type 1 error to beyond 0.05, right? So you can see this in many published studies. So here's one published study which carried out 145 statistical tests on the same data set, and they kept the alpha value at 0.05 for each of those tests. Here's another paper where they carried out 20 statistical tests, and same thing, they held the type 1 error at 0.05. Here's another test. This is actually from my own paper when I was a graduate student. I wrote this paper. I carried out at least 18 tests, probably more. And again, I was acting as if I had done only one test, and my type 1 error was held at 0.015. So what's wrong with this is that when you carry out more than one significance test, null hypothesis significance test, you are going to inflate your type 1 error. And it's pretty easy to see theoretically what's going on here. Okay, so imagine that we carry out 3 hypothesis tests. Okay, so we run our first test, and the type 1 error, the probability of incorrectly rejecting the null in the first test is alpha here. So 1 minus alpha is the alternative, right, in this probability space. Then I carry out my second test. In my second test, the branching of the probability space goes like this, right? I could again have a type 1 error of alpha here, and 1 minus alpha here, and alpha here, and 1 minus alpha here, right? Let's say I carry out a third test now, okay? So again, the probability space explodes again. I've got alpha, 1 minus alpha here, 1 minus alpha here, and similarly, same situation here, right? So 1 minus alpha, alpha, and this would be, I'm running out of space here, but let's do it like this, 1 minus alpha and alpha, right? So now you can ask the question, right, what's in these 3, when you do these 3 statistical tests, what is the probability of rejecting at least one null hypothesis incorrectly? Okay, so, well, what would that be? So the probability of rejecting at least one null hypothesis incorrectly would be everything except this path, right? Every leaf in this tree except this path would be a possible way for us to reject at least one null hypothesis incorrectly. So if I sum up all these probabilities in the leaf of this probability space, those summed up probabilities are going to be larger than 0.05. That's how the explosion in type 1 error happens as you increase the number of statistical tests. So the story gets even worse, right? So if you carry out, let's say, 100 tests, and I just showed you an example of somebody carrying out 145 tests, right? Once you carry out 100 tests like this, this probability space is going to get larger and larger, and the probability of your incorrectly rejecting at least one null hypothesis incorrectly will be 100%. So let's look at the inflation of type 1 error under repeated statistical tests on the same data set. Now, suppose you did a statistical test only once. Every time you ran the experiment, you do only one statistical test. What would be the type 1 error? We can establish this with simulation. So we're going to do the experiment 1000 times, and each time you're going to take a sample from a standard normal distribution. That means a distribution where the null is actually true, mu is equal to 0. Carry out the t-test on the sample that we take, extract the p-value and save it in a vector, right? So our goal here is to obtain 1000 values of p-values and find out which proportion of these p-values is less than 0.05. Those would be the instances where we made a type 1 error, right? So we are calculating the mean proportion where those p-values are less than 0.05, and the number is approximately 0.05. Of course, this is a simulation with 1000 values, so there will be small fluctuations in this number, but it's approximately 0.05 here, right? Now, if I were to run the same simulation, but this time I would carry out 2 statistical tests each time, right? What would happen to the type 1 error? So what I'm doing here is that I'm carrying out 1000 times, I'm carrying out 2 statistical tests, okay? And what I'm then doing is I'm saving not one p-value in each of the 1000 simulations, but 2 p-values here, right? And in each of these statistical tests, the null is actually true. So now the question that we want to ask is, in those 1000 simulations, what is the probability that at least one of the 2 statistical tests came out significant, right? So that's what the calculation is that I'm doing here. I won't bother you with the code, but the upshot is that the probability is now, the type 1 error is no longer 0.05, it's 0.10, right? So it's going up, and it's going to keep going up the more the number of statistical tests I do. And we can actually visualize this quickly. If you look here, what I'm doing here is I'm increasing the number of statistical tests that I'm doing and computing the inflation in the type 1 error. And you can see that the type 1 error is inflating, going up all the way to 1 once I've reached about 100 statistical tests, right? So this is called the multiple comparisons problem, and it's a very serious issue, because if you carry out hundreds of statistical tests, you're guaranteed to get something coming out significant, even if the null hypothesis were true in all the cases, right? So you can end up with significant results that don't actually mean anything substantive for our scientific question. That is really bad news. The solution to the multiple comparisons problem is pretty straightforward. There are several ways to do this, but one sensible and easy and conservative way to do this is to do something called the Bonferroni correction. If you're going to do n statistical tests, then divide your alpha of 0.05 by n, and that's your new alpha. That's the new standard that you have to meet to declare significance in your collection of statistical tests. Okay, so with the Bayesian data analysis, the situation can be slightly different depending on what kind of Bayesian data analysis you're doing. If you're a classical Bayesian, there's no concept of type 1, type 2 error. The data are what they are, right? There's no replicability implied in the data set that you have collected. And so you're just going to be drawing inferences from what data you've collected with no implication about the repeatable properties of the data under hypothetical repeated sampling. Of course, even Bayesians can think in this frequentist way and think about the repeatable properties of their experiment designs and therefore of their Bayesian analyses and the statistics that they compute in the Bayesian setting. Now, in those situations, Bayesians, if they're thinking like frequentists, they would also face the same type of multiple comparison problem. Can't get away from this problem if you're thinking about, the replicability properties of your experiment. And for people like us, psychologists and linguists, every experiment that we do, we implicitly assume that that experiment is replicable, right? So the replicability properties of an experiment design are very important to people working in experimental settings in linguistics and psychology. So this multiple comparisons problem is something that we have to grapple with whenever we do data analysis, regardless of whether you're a Bayesian or a frequentist.